Hey, good morning, good afternoon, everybody. Hello from Madrid. So first of all, I want to thank the organizers for the very kind invitation. It's really a pleasure to give a talk at Princeton, although virtually this time. So I'm sorry I cannot be there, but I'm pretty sure there will be more opportunities to visit in the future. So I'm going to talk about this topic, the many and different, also facets of complexity of Beltrami fields in Euclidean space. So my talk is going to be very expository, so I'm not going to give any proofs, just well, statements, claims, and ideas and tools that are important to prove some of the theorems that I'm going to state. And actually, I'm going to spend some time, a few slides, 6 or 7 slides, motivating a bit the problems, introducing the concept of Beltrami fields, because maybe not everybody is familiar with these objects. And of course, you can interrupt me during the talk to ask questions. If you interrupt many times, the problem is that I may not finish the talk, but it's not a problem. It's up to you, of course. Okay, so let's start. So Beltrami field. So what's a Beltrami field? This is the definition. So the definition is very simple. So it's a vector field in dimension 3. I'm going to consider only 3-dimensional spaces that satisfy this PDE, this partial differential equation. The curl of U, curl is the usual rotational operator in vector calculus, vector analysis. It's equal to lambda U, is proportional to the field itself, and this lambda is a constant. I'll consider only a constant factor Beltrami fields, which is different from 0. As I said, as is contained in the title, I'm going to focus only on Beltrami fields in Euclidean space, so R3 endowed with the Euclidean metric, or also I will say a few facts and results about Beltrami fields in R3 with periodic boundary conditions, so the standard flat torus, R quotient 2 pi z to the third power. So some basic properties of these objects. Of course, you can define this on any 3-dimensional Riemannian manifold, even higher dimension. But in higher dimension, you have to define the curl in a different way. But just focusing on the Euclidean case, these are the basic properties of these objects, of these vector fields. Of course, if you fix lambda, for each lambda, this is a linear equation, of course. That implies if you take divergence at both sides of the equation, the divergence of the curl is always 0. So since lambda is a constant that is non-zero, this implies that the divergence of U is 0. So any Beltrami field, the consequence is that any Beltrami field is divergence-free. A second fact is that Beltrami fields are very smooth. Actually, they are analytic, real analytic. This comes from elliptic regularity estimates, standard estimates. A third fact is that for each lambda, different from 0, the space of Beltrami fields is huge. It's infinite dimensional, actually. So you have many Beltrami fields, and even on the torus, on T3 is not infinite dimensional, but on T3 the spectrum is discrete. You have infinitely many values of lambda for which this has solutions on the 3 torus. But this infinitely many values only accumulate at infinity, plus and minus infinity. And even the multiplicity, even given the fact that the multiplicity is finite, for each eigenvalue, it increases. When lambda tends to infinity, the multiplicity also tends to infinity. So as lambda tends to infinity, you have a bigger and bigger space of eigenfields. You have to understand this equation as an eigenvalue equation or an eigenfield equation on the torus, or even in R3. Although in R3, of course, you don't have to understand this as a discrete spectrum. And the final observation, which is also well known, is that Beltrami fields in Euclidean space do not have finite energy. They are not in L2, and but they can decay. There are many examples of Beltrami fields that decay, and the sharp decay, the best decay that you can have for Beltrami fields in R3 is 1/x, the inverse of the distance to the origin. This is the best decay of Beltrami fields in Euclidean space. Okay, so these are the very basic properties of these objects. So let's motivate or let's introduce where these objects appear. So they appear in several contexts. Probably the most important one is in fluid mechanics. So they are stationary solutions of the Euler equations. So ideal fluid flow, so inviscid and incompressible in equilibrium. So this means that solutions don't depend on time. So these are the stationary Euler equations. So this is the covariant, yes. So this is the covariant derivative of u along u, and this is the gradient of the pressure. Divergence of u is equal to 0, and you can check very easily that any vector field that satisfies this equation, curl of u equal to lambda u, satisfies this equation for a pressure function, a hydrodynamic pressure, which is given by this formula, -1 square is the pointwise norm of u using the Euclidean metric, of course. So they are stationary solutions of Euler. And actually their relevance goes beyond the fact that they are a special class of stationary solutions of Euler in Euclidean space. I will compare with other stationary solutions later, introducing something that is called the Arnold's structure theorem. But at this moment, I want to emphasize also that more generally, these Beltrami fields form a basis, a natural basis for divergence-free vector fields on the three top zero mean. So this means that any divergence-free vector field W with zero mean means that each of the three components of the field integrate to zero, simply this. So it's a superposition. You can write it as a superposition of Beltrami fields. So you have uj and usj, and this is a basis of Beltrami fields on the torus. These are some constants, and this basis corresponds to the eigenvalues of the curl operator. You have, remember, you have an eigenvalue problem on the three torus, and you have that this lambda belongs to a discrete spectrum. So lambda 1, lambda 2, lambda minus 1, lambda minus 2. This is negative, this is positive part of the spectrum. And the main conclusion is that you can write any W in this basis of Beltrami fields. And the convergence, it's, well, in L2, of course. But if W turns out to be in a Sobolev space for some regularity, okay, then the convergence actually is in HK for any Sobolev norm. And so then the conclusion is that this is the vector analog of the usual basis of complex exponentials. When you do Fourier analysis, you expand functions in the basis of complex exponentials on the torus, for example. And then the analogous in the case of vector fields, if you want to study divergence-free, not any vector field, divergence-free vector fields on the two torus, it's natural to expand it in this basis of Beltrami fields. So this is not only an observation that it's natural, or it's, let's say, relevant for the spectral theoretic interpretation of Beltrami fields, if you want, or for comparison with eigenfunctions of the Laplacian on manifolds. But this superposition property of Beltrami fields has been also useful to construct time-dependent solutions in hydrodynamics that exhibit very interesting or even remarkable features. Just to mention two, of course, famous Delelis and Sekelichidis construction of Helder solutions of a time-dependent Euler equation that dissipate energy. This was Onsager's conjecture for different values of the modulus of continuity. And also, you can construct smooth solutions of Navier-Stokes equation that exhibit a finite cascade of topological vortex reconnections. This is something we did with Alberto Enciso and Renato Luca a few years ago. This is a nice picture of what I mean by topological vortex reconnection. This is taken from an experiment, a very famous experiment of William Irwin and his team in Chicago. And so you have vortices, which is something. It's so vortex lines are the integral curves of the vorticity vector field. So you have here this zoom image of these vortex lines. And when time passes, you have that these lines collide, and after this collision point, they break and they reconnect and they change their topology. And this is due to the fact of the presence of viscosity. So the moral is that these Beltrami fields, just to summarize, Beltrami fields in hydrodynamics are not only relevant because they are, of course, stationary solutions of Euler equations, but they are building blocks to construct other interesting solutions of even time-dependent Euler equations or Navier-Stokes equations. Okay, so this concerns hydrodynamics, but Beltrami fields also appear in other contexts of physics where they are also relevant. So in the context of MHD, in magnetohydrodynamics, they have a different name. They are known as force-free fields. So the reason is that if you have a magnetic field V that satisfies the Beltrami equation, curl of V is equal to lambda V, then something that is called the Lorentz force, which is the force that V produces on the, let's say, on the plasma that is creating this magnetic field, is J cross V, this vector product. J is the current, is the plasma current, which is created by the magnetic field. By Maxwell equations, J is actually proportional to curl of V, to the rotational of the magnetic field. So then this Lorentz force is equal to 0 because you are considering magnetic fields for which curl of V is proportional to V. So they are parallel, they are collinear, so this is 0. And that's why in this context of MHD, they are called force-free fields. They don't exert, they don't have any force acting on the plasma itself. Okay, that's the reason of this name. And they model MHD equilibria. Of course, they are stationary solutions of the MHD equations in stellar atmospheres, in plasmas, etc. So this is a nice picture, for example, of the solar corona, a magnetic tangle. This is a magnetic tube. You have two disks here over the surface of the sun, and you have this tube that joins these two disks. And actually, this is a zoom of the tube here. You have the lines of the magnetic field that go from below to the top, and there are some problems related to the topology and to the structure of these lines. So this is concerning this MHD interpretation, but there are many reasons for which force-free is important in MHD, in magnetohydrodynamics. One of the most basics probably is that from the energetic viewpoint, they are optimal. They minimize energy in some sense. So to be more precise, if you consider a bounded domain of R3, let's assume for simplicity that it's simply connected, although it's not important, this assumption. Then Beltrami fields are optimal from the energetic viewpoint, as I said, in the sense that if you minimize, so let's look at the energy of the field, the L2 norm of the field, right? The B square integrated over omega with a constraint that this helicity is equal to constant, then the infimum, the minimum value among all fields that are in L2 and that are divergence free and that are tangent to the boundary. Sorry, is there some question in the chat? Now I'm seeing that there is something written there. I'm not sure.
Yeah, it's a question. Just
sorry, I cannot see the chat, so maybe if you can read the.
I cannot see it. You can see it from there.
Or maybe I can try, but if I do it, okay, let's try. Let's see. Okay. Are you okay, Chris Krylova? Are you limited to T3 in this construction due to physical implications, or are there mathematical challenges that arise trying to go to higher orders? Okay, T3 is so as I said, I'm always considering Euclidean space, so R3 or T3. You can in this construction, I'm not sure which construction you refer to, but you can define Beltrami fields on any Riemannian free manifold. Eva already talked about this yesterday. So yes, in principle, you can consider some of these constructions on any Riemannian free manifold. And if you want to go to higher dimension, then it's more complicated because, well, it's like if you compare contact topology in dimension 5 and in dimension 3. I think there is a difference, although I'm not an expert on the subject. So it's the same. The equation becomes non-linear in higher dimensions. So everything becomes much more complicated if you want to understand these problems in dimension 5, for example. But in principle, you can ask the questions there. Yes. Is this the question, or more or less? Yeah.
Yes.
Okay. Okay. So as I was saying that so Beltrami fields are optimal from the energetic viewpoint. They minimize the L2 norm. Here there is a very natural constraint. This constraint arises from the MHD evolution, ideal MHD evolution, because during the evolution the magnetic field is transported by a flow, and we know that helicity is invariant by volume preserving transformations. So okay, so I'm not going to say more about this, but just it's important to have in mind that Beltrami fields are very special from many different viewpoints. And helicity, I'm not going to define it. This is a functional acting on the space of divergence-free fields. It's defined this way. It has a nice interpretation related to linking number or asymptotic linking number in some average sense, but I'm not going to comment about this more. Just what I want to comment now is that these questions in MHD, and actually this optimality property that is very basic, is related to famous and important problems in plasma physics. One is Taylor relaxation hypothesis, which roughly speaking says that a magnetic field under ideal MHD evolution relaxes in some sense to a Beltrami field. And other question is Parker's problem, which is very interesting, and which is related to the transition map in a magnetic tube, and the hypothesis and the problem, or the conjecture says that a generic transition map cannot be realized by a force-free field. A transition map is very easy to understand. You have this tube, right? You have a tube. Let's just consider a cylinder. Okay, so you have the bottom disk and some top disk, and you have lines going from bottom to top, right? Simply this, a field of this type, So the transition function, or Poincare map, if you want, is the map that takes a point here and assigns the point on the top part of the cylinder, just following the flow, right? So this Parker's problem is.
There's a question.
Yes, question.
Yeah, yes, with regard to the Taylor relaxation hypothesis, are KAM tori an obstruction to that?
For Taylor relaxation hypothesis?
Yes. Well, if the magnetic field lines follow a torus.
The hypothesis, as I stated here, is known to be false. I mean, there are examples. You can construct examples of divergence-free fields and domains that cannot relax to force-free fields, to Beltrami fields. So in the case of KAM tori, or if you have some KAM surfaces, this can be in principle a stationary solution of the Euler equation. It could also be a force-free field, because there are Beltrami fields that also have KAM tori. I mean, it's not force-free fields are not ergodic necessarily. But no, the structures I know, or the counterexamples I know to these, they don't come from KAM surfaces. No.
Thank you.
But actually, there are generalities of these problems or of these conjectures, which is instead of considering relaxation to Beltrami field comes from the fact that it minimizes energy. So, okay, it's natural to think that you could achieve the minimal value, but there are some generalizations which ask about relaxation to equilibria, to MHD equilibria, much more general than Beltrami fields. Okay. But in any case, with this, I just wanted to emphasize that these objects appear in many contexts. So just now, to finish these preliminaries about motivation and about the subjects where this appears. Just I want to comment about contact geometry, just one slide, because Eva already talked a lot about this yesterday. So if you consider the metric dual one form, alpha, the dual to the field, to the vector field, then the Beltrami equation in terms of forms, Eva already wrote this yesterday, is d alpha, the exterior derivative of alpha, is equal to lambda, the constant, star alpha. Star is the Hodge-star operator. So then, if the vector field, the Beltrami field, doesn't vanish, of course, alpha is a contact form, because if you take alpha, wedge the alpha here, you get here alpha square, the modulus of alpha square, which is modulus of u square, and then it's non-vanishing by the assumption. So it's a contact form. And actually, of course, as Eva said yesterday, if you reparameterize the field u over u square, and this makes sense because u doesn't vanish, then this new vector field R is actually the rep field of the contact form alpha. Okay, it satisfies the definition of a rep vector field. And the converse is also true, as Eva explained. We know after Sullivan and also Nara and Rice, who developed this substantially, that for any contact form alpha, there exists a metric. There exists many metrics, but one metric, which is another metric, that makes the rep field Beltrami with respect to such a metric. So, and it satisfies this equation with a factor 1. Well, if you define the metric in a different way, you can get here a different factor. That's not important. But this connection is what is very useful to prove, to obtain several constructions in this context. But as I said, I will focus only on Euclidean space, R3 or the 3 torus. So for the application of the power of these ideas, of the power of contact geometry in this setting of Beltrami fields, just you have to remember Eva's talk yesterday, or if you miss it, you can, I guess you can go to YouTube and you can see it, you can watch it there. Okay, so
yes,
question.
There could be also singularity in this field, right? So it could be vanished and there are zeros could be.
If it could have zeros, you mean?
Yes.
Yes, the Beltrami fields.
Is there some normal form or something near this?
Near the zero sets. I don't know a normal form. Of course, it's divergence-free, so this limits the sort of singularities. And generically, okay, and you can prove also that generically the singularities are hyperbolic. That's also true. And yes, you can give normal forms for the linear part. Yes, that's easy. But then, if you want to prove some linearization theorems, you have to impose some conditions on the arithmetics of the eigenvalues. But as for any divergence-free field, yes. But yes, I would say that there are some generic normal forms, but not for any sort of singularity. I mean, it's just for the generic singularities. Yes, that's true. That's true. But so then, if the Beltrami field has zeros, which may have and actually typically has, so with probability 1, in some sense, a Beltrami field has zeros. That's a theorem that you can prove in giving some precise meaning to genericity here. It's true that the zeros, although they don't need to be hyperbolic, they cannot be, for example, they cannot be very wild in the sense that the dimension is at most 1. For example, you cannot have surfaces of zeros. That's something that can be proved. And of course, it's analytic. Your vector field is analytic. So the zero set is an analytic set, which means that it has some stratification properties, etc. So still, even if you don't assume a hyperbolicity of the zeros, it still is not so bad, the zero set, because of the analyticity in the Euclidean setting. Okay. So complexity. So what about complexity? So that's the goal of the talk. So so among stationary Euler flows, we already saw that they are stationary solutions of the Euler equations. They are very special. in the sense that they are the only ones, okay, it's not completely right, but let's put it in a simple way. They are the only ones that can exhibit complexity. And the reason is this theorem of Arnold, a beautiful theorem of Arnold, proof in 1965, which is that a generic, okay, now I'm going to talk a bit more about this generic, what this means. A stationary solution of the Euler equations on a bounded domain omega that is not Beltrami, it's integrable. So by integrable, it's meant the following, that the domain is a union of subdomains that are covered by invariant tori, something like this, or also invariant periodic cylinders like this. And then the lines, the integral curves of the field on the cylinders are always periodic lines, okay? The boundary of the cylinder is touching the boundary of the domain omega. And inside, in the interior region of the domain, you also can have invariant tori, and of course the flow on this tori is linear. It's conjugate to a linear flow, rational or irrational. So by generic, I mean, okay, the original Arnold's theorem is in the analytic setting. So it considers stationary solutions of the Euler equations that are real analytic. However, that's not very important. Well, that's not important at all. You can assume, you can prove exactly the same result if you assume some generic property on the critical set. Say on the critical set of what? On the critical set of something that is called the Bernoulli function. The Bernoulli function is an object that is important in fluid mechanics for stationary solutions, and it's a first integral. Bernoulli function is a first integral of a stationary Euler equation, of a stationary solution of the Euler equation. So for Beltrami fields, the Bernoulli function is a constant, is identically constant. But for more general stationary solutions, Bernoulli function does not need to be constant. And if you assume genericity on this Bernoulli function, which means Morse-Bott, for example, that is Morse-Bott, or it has some stratification property on the critical level set, etc., then this theorem holds true. Okay.
Not Beltrami means it's nowhere Beltrami, right?
It's nowhere Beltrami, right? So then this raises the very interesting question of whether there exist solutions where Bernoulli function is constant on some domains, which means Beltrami on some domains, and non-constant on some other parts. So these solutions exist. These solutions exist on S3 for sure, on the 3 sphere, and also on R3. But actually on R3, the only solutions that I know of this type are axisymmetric. So then, but not very complicated, because any divergence-free axisymmetric field is integrable in Euclidean space. So, but a priori, in principle, you could have some regions of Beltrami behavior, let's say, which exhibit complicated behavior, and some other integrable regions. That's a priori, that's possible. Okay, so in contrast, yes.
If I ask, because the Bernoulli function is real analytic, so how can it be constant in some open set and then non-constant?
No, of course. If it's under the assumption of the original.
Because you said on S3, for instance, it's real analytic, right? If you take it.
No. Okay.
So, Beltrami, where it's not Beltrami.
Okay, so the Bernoulli function, there is no the regularity of the Bernoulli function can be anything. I mean, the point is what you assume to prove your theorem.
Only when it's Beltrami, okay.
Yeah, so Beltrami means that the Bernoulli function is constant. That's even you can define Beltrami fields, but then this would be a more general definition of Beltrami field, right? But so analyticity, maybe I didn't explain it correctly, or I didn't explain myself. It's when I mentioned analyticity, this was the assumption in the original formulation of Arnold for this theorem. So erase generic here, and you can write an analytic stationary solution, etc., etc. But I mean, that's an assumption. You may have, and you have, many solutions with Bernoulli functions that are not analytic, that are only C infinity. And for these examples, you can build with your hands actually an example where your Bernoulli function is constant on some domain, on some let's say solid torus, and it becomes non-constant outside. Of course, this is not analytic, but it's smooth, or the construction can be made smooth. Okay, is it clearer now?
Yes.
Okay. So, but Beltrami fields, as I said, they can be very complicated. So probably the very first examples of complexity in Beltrami fields, of some sort of complexity, is the ABC flows. The ABC flows on T3. I didn't write the formula here. I'm sorry. Now I'm realizing that maybe I should have written it. It is very, very explicit. It's just sines and cosines. It corresponds to the lowest positive eigenvalue of the curl operator on the free torus. So it's just a three-component field, and it's sines and cosines. And ABC means that you have three parameters, three free parameters, A, B, and C, real numbers. Okay. So for some values of the parameters, you can do numerics, and you can do, for example, Poincare sections and all these things. And you see a complex behavior, typical structure of chaos. You have, yes, of course, invariant tori, but you also have some homoclinic intersections or chaotic, in some sense, invariant sets, etc. So, yes.
The dimensions of the torus?
This on the torus, yes.
The
Right.
size of the torus.
Ah, the size. No, that's not important. I'm considering 2 pi, just R3 divided by 2 pi.
You don't get anything different if you change the size of the dimensions of the torus? That would change the eigenvalue.
Yeah, of course, it changes the eigenvalue, but it's an easy change. I mean, if you okay, let's. Okay. Yeah, well, that question is interesting in one sense. Okay, I mean, I put here 2 pi just so that sine of x is in this space, but of course you can put here any constant, and then it's just a reparametrization of sine of x. It's just multiplying or dividing by the constant. But what is interesting is that you could, of course, consider other lattices, right? So you could consider the quotient of R3 with a lattice that is not this, let's say, orthogonal lattice. You could consider other lattices, and this gives you other tori, right? They're all of them flat tori. So this may make much difference depending on the lattice and depending on arithmetic properties on the lattice. Of course, the spectrum changes. Of course, that's clear, and you can. I mean, you can compute. Well, you cannot compute, but you can write how you can compute the spectrum. It's related to certain quadratic forms to be equal to some constants, etc. But the properties of the lattices certainly affect many properties. Many high energy properties of the fields. That's true. That's true. But if your lattice is changed simply by multiplying by a constant factor, this is not important. I mean, it changes the eigenvalues, but it's an easy change.
Do the eigenvalues change continuously with the lattice?
Continuously with what?
With changing the moduli, the lattice.
Of the lattice?
Yeah.
Okay, no, the eigenvalues, no, they don't change. They typically they split, for example, the multiplicity. So you have for the standard torus, you have eigenvalue whatever has multiplicity 27, say. But if your lattice, you move slightly your lattice, since irrational numbers are dense, have full measure in rational, you split everything, and actually all the multiplicities become finite. All the multiplicities become finite. So it's not a continuous dependence. No. But of course you have some convergence of many spaces that are associated to different eigenvalues. Of course, may converge in some sense to a single bigger space, eigenspace. Okay, this sort of standard things, but it's not continuous. No, it's you split many things. Yeah. So this concerns this, but and actually these numerical experiments were already done by Michel Lennon. So Michel Lennon, so he was he was a colleague of Arnold. So Arnold was at that time, I think, in Observatoire de Paris, and he knew how to do numerics, and he was the first one, I think, to do numerics with the ABC flows, with the ABC for some specific values, of A, B, and C of these constants. So this led Arnold actually to speculate, to suggest about the complexity of Beltrami fields. So this is what he wrote, that so it's probable that that these Beltrami fields, curl of u equal lambda u, exhibit streamlines of complicated topology, and these complexities are similar, should be as those that appear in celestial mechanics. So by this, what is meant is that is this typical picture of a 3D or let's say of a 2 degrees of freedom Hamiltonian system restricted to an energy level set. If you take a Poincare section, this is a typical picture that you observe. So you have, of course, Km tori. Km is there are usually there are Km tori, right? The generic thing is not having neither ergodicity nor total integrability. It's a mixture of both things, Km tori with chaos in some sense. So, so you have the Km tori, but you also have these complicated sets which come from something called homoclinic intersections. And this, which is very well known in the context of Hamiltonian system, should also appear or should also be there in the context of Beltrami fields. So just I want to share this last observation. It's very intriguing, very interesting. I don't know much about this. So there is some numerical evidence. So this is more for people who are more interested in fluid mechanics. Numerical, I'd say maybe also experimental in some experiments, of a phenomenon that is called Beltramization. This is, if you type in Google this word, Beltramization, there is literature about this. So apparently the definition of this phenomenon, say, is that velocity and vorticity tend to align in turbulent regions of the fluid with low dissipation. So low dissipation is Euler equation, say, and turbulent region is complexity, say. So and this alignment between velocity and vorticity is precisely Beltrami equation. So then this raises the question of what is the role of Beltrami fields in turbulence, in Lagrangian turbulence, wherever this means or wherever you define it. Okay, so now I think we are ready to state some of the theorems that we proved in this concerning this complexity. So the first question is, okay, just in short, is a typical Beltrami field chaotic? So what do I mean by chaos? So I mean the existence of invariant set, compact invariant set, which is chaotic and which is called horseshoe. This is a very well-defined object. So the transverse, so you have, if you have a flow with a horseshoe, this invariant set, the transverse section of the invariant set is not like a very nice submanifold, etc. It's you have a Cantor set. It's a square Cantor in this case, and the dynamics on this square Cantor is well, apparently it's very simple. It's a shift or a subshift, but the dynamics of the shift on the square Cantor set turns out to be complicated. It's okay. It has infinitely many periodic orbits, topological transitivity, etc., and you have also hyperbolicity, etc. So, so these objects, these horseshoes, these compact invariant sets, we know after the remarkable works of Katok that in the case of 3D, this is only true in dimension 3 and for flows, for vector fields, conservative, you have equivalence between existence of a horseshoe, of a set of this type. Also, this is equivalent to positive topological entropy, but this is also equivalent in this dimension to existence of transverse homoclinic intersection, which was this objects here that appeared, the intersection between two. You have two stable and unstable components associated to a periodic orbit or to a fixed point in the case of the map that intersect, but they do it in a transverse way. So everything is equivalent in this dimension 3, not in higher. So with these objects in mind, these horseshoes, we can introduce this definition. So given a Beltrami field U, we denote by NHR the number of horseshoes of U contained in the ball of radius R, the number of these compact invariant sets in the ball of radius R. So the theorem that we proved recently with Alberto and with Álvaro Romaniega, our PhD student, is the following. So we proved that with probability 1, and now I'm going to explain what we mean by probability, how you introduce probability in this setting. A random Beltrami field on R3, this is in Euclidean space, satisfies that the number of these compact invariant sets in the ball of radius R grows volumetrically. Okay, there exists some constant here, it's positive. It's you can do some numerical estimates of the value of the constant, but not sharp at all. It's a lower bound, so it could increase more than this. But what is sure is that with probability 1, if you pick randomly a Beltrami field, then it will have infinitely many horseshoes, and the way these horseshoes are distributed on space is volumetric. Well, at least volumetric is a lower bound. In particular, of course, since each horseshoe has positive topological entropy, the topological entropy is positive, almost surely, of a Beltrami field, of a random Beltrami field. Okay, so this is the result. This is the theorem, and here, of course, it's key to define. So, what do we mean by a random Beltrami field? What's the probability measure that you introduce in this space of Beltrami fields? So, unfortunately, I'm not going to define this in a very precise way. It would take too long, actually a whole lecture for this. But just I will mention that as I said, we define a probability measure, mu b, which is Gaussian probability measure on the space of vector fields, of CK vector fields in R3. You fix any k that you want. We fix k equal 4 or 5 because we want to apply K-and theory at some moment. And this probability measure satisfies very nice properties. So, for example, for each point, if you consider the density function, the probability density function of each random field, of a random field at each point x, you fix x. So this gives you u of x. This is then a vector in R3, right? Then the probability density function is just the Gaussian probability of zero mean, and of variance equal to 1. Okay. So if you want to compute the probability of your random Beltrami field to have values at a fixed point x, to have values belonging to a certain ball of R3, you just integrate this density function over this ball. Okay, this gives you the probability. If you integrate this over the whole R3, this is 1, of course. But a very important, of course, property of this measure, of this probability measure, is that the support of the measure is precisely the space of Beltrami fields. So you fix, we are fixing here lambda, the eigenvalue, lambda equal 1, for example. This is not important. And then this linear space of Beltrami fields of eigenvalue line is precisely the support of the probability measure. And finally, another important property is that the density, the measure, the probability measure on this space of vector fields is translational invariant. This means that the covariance kernel of which is a matrix, a 3×3 matrix, of this density, of this probability measure, it depends just on x minus y. It depends on the difference, so it's invariant by translations. And actually, the action of translations is ergodic. It's ergodic in this space with this probability measure, which allows you to prove to use ergodic theorem. Okay, so this is the theorem that we prove. As I said, I'm sorry, I'm not going to talk about proofs in this talk. Actually, defining the probability measure takes some time. It takes several slides. But what I want to comment now, I want to emphasize now, it's a tool, a key ingredient. So I'm going to emphasize this because I think it, since this is a workshop on H principle, convex integration, and this stuff, this could be of interest to this tool, and a comparison with a different tool in another context could be of interest to people that are working in this workshop. So we use in the proof, one of the ingredients, actually key ingredient, is this let's say sort of flexibility, this approximation theorem that we proved already 10 years ago, which is the following. So it's an approximation or an extension theorem. So if you have V, this is a Beltrami field, but it's not global. Just you have this vector field defined on certain bounded domain of the space, on omega, and you assume some topological property. The complement, you assume that the complement of omega is connected. Then what we can prove is that for any epsilon and any integer k, and any compact set k contained in omega, there exists a global Beltrami field U satisfying K of U equal lambda U in R3 that decays in the optimal way. So as 1 over x, that's the optimal decay. That approximates V in the compact set K. So the difference, the CK norm, is epsilon, and this is for any epsilon for any K. So this allows you to construct, to do local constructions, say, which always a local construction, a local solution of a PDE is much more flexible in general than a global solution. So you can do local constructions and you can then approximate by global objects. And then this allows you to prove some global properties of the solutions. So just I want to emphasize here the following. The proof is very linear, so it makes use of Green's functions of the Kell operator in Euclidean space, etc. So it works for linear equations, not only actually for Beltrami fields. You can do this scheme for other equations, but it's very linear. But I want to compare here with this very interesting theorem, proof in a totally different way using the convex integration scheme introduced by the Lattices and Székely-Hidi. This concerns stationary solutions. So in a paper a few years ago, Chofrut and Székely-Hidi, they extended the Lattices and Székely-Hidi formulation as a differential inclusion of Euler equations. They did it for stationary solutions. So as a consequence of this, you can prove the following result. So if you have now you have a vector field V, let's say C infinity, which is a stationary solution of the Euler equation on a bounded domain, not necessarily Beltrami, any stationary solution of Euler. Then something similar. So you have for any epsilon, there exists a global solution of Euler, stationary solution. Now it's not smooth. This is a difference. It's in L infinity, and it's a weak solution, such that it approximates your local solution V in a very weak norm. So in H-1, for example. But actually, this U is not only in L infinity. It's compactly supported. It's supported in a neighborhood of this set omega. So I wanted just to write these two statements because I think it's interesting to compare on how different techniques can yield to results which are of approximation type, and because I think it can be interesting for people there who are working on convex integration. Okay, so but now finally, just my last 10 minutes probably. I'm sorry, I think I spent too much time before. Usually happens. I want to talk about a different facet of complexity, which is computational power. This maybe I can skip some of these things, or I can go very fast because Eva already talked about this yesterday, about Chris Moore question in 1991, if there exists a solution to the Euler equations that can simulate any computer algorithm, and in case such solutions exist, there is Terry Tao proposal of trying to construct or trying to use this computational power to create initial data that are programmed to blow up. But to make this precise, we need to define what's a computer from the mathematical viewpoint. The mathematical description of a computer algorithm is well, there are several, there are many, but the one that we're going to use is Turing machines. And the concept of universal Turing machine, it's a Turing machine that can simulate everything. Every other Turing machine is inside this universal one. And just for this, I need to define what a Turing machine is. So Turing machine is the following. So it consists of the following data. So you have Q. Q is a finite set of states. Let's say A, B, C, and D, 4 states. And among these states, there are two that are very special. One is Q naught, that's the initial state. Any initial input of the Turing machine will have this Q naught. And then the Q halt. The Q halt will tell you when the Turing machine has finished the computation, when it halts the algorithm and it gives you the output. And then there is sigma, which is the alphabet, usually 0, 1. And the transition function. The transition function, it gives you the dynamics of the Turing machine. Is a sort of dynamical system. So it's a function from Q times sigma to Q times sigma minus 1, 0, 1. So this minus 1, 0, 1 means shift to the left, shift to the right, or no shift if it's 0. So the input of a Turing machine is the current state Q and the current tape. The tape is an infinite sequence of zeros and ones, say. So it belongs to sigma set. And this is the way the Turing machine works. So you have the tape here, right? 1, 0, 1, etc. You have the state Q and the delta will tell you how this runs. So in the case you have reached the Q halt state, then halt the algorithm, you stop, and then you return T as the output. Otherwise, you compute the delta, the transition, which gives you another state, another 0 element of the tape, the element in the zero box of the tape, and then a shift, and then you replace Q by Q prime, etc. And you continue running the algorithm, right? Till you reach the Q halt, or maybe not, maybe it runs forever and it never halts. That's the halting problem. So the interesting point of Turing machines is that there is a well-developed and actually I'd say standard for people in computer science and the dynamical systems and the connections with dynamical systems of what one means by a Turing complete dynamics, or by a dynamical system to simulate a Turing machine. So we say that a vector field X is Turing complete if you have the following. So for any integer K, so you given any Turing machine T, any input tape T, and any finite output part of the output, the minus k part, then we say that X is Turing complete if there exists an explicit point associated to all this data, and an explicit open set associated to all this data, such that the orbit of X through the point intersects U if and only if the Turing machine holds with an output with this input at an output tape whose positions correspond to these symbols. So somehow, given the input, given the output, the vector field, what is doing, the vector field is encoding the dynamics of the Turing machine in this specific trajectory, which starts at the point P, and then it reaches the set U or not. And then depending on whether U depends, so P depends on the input tape always. It might depend on the output or not, but if it depends on the output, then U is fixed. It doesn't depend on the data of the problem. So depending on, depending on whether P or U, how they are constructed, you get different notions, but the definition is always the same. Simply you have that the dependence of U is on the whole data, or just on part of the data. So this is what we mean by Turing complete dynamics, and this is the theorem that we proved very recently. So recently that is not yet on the archive, but it will be in maybe 1 week or in a few days. So we proved that there exists a Beltrami field in Euclidean space that can simulate a universal Turing machine, and simulation in this very precise sense. So it is Turing complete. Okay. So in particular, it implies, but this was already mentioned several times by Eva yesterday, there are some consequences about undecidable trajectories. So, but now I want to comment about two properties of this field. One property is that actually all the computations of the field, so the field simulates a universal Turing machine, right? So this means that the universal Turing machine is encoded into the dynamics, into the integral curves of the field. So on which integral curves this is encoded? Just on those that are on a certain invariant plane. So this field has an invariant plane, is tangent to a certain plane, and all the computations take place there. And there is a second property which is important, mainly this estimate here, which is the weakly robustness of this computational power. So this means that if you perturb this vector field, it's still Turing complete as far as your perturbation decays fast enough at infinity. So it's not a uniform perturbation, it's a better than uniform. And the estimate for this decay is a double exponential. So any field that it's close to you with this double exponential error will be also Turing complete. Okay. So now I have to finish, I think. But okay, there is a second ingredient, which is global Cauchy-Kovalevskaya, which is used, but I'm not going. But I think it's interesting to comment about finite energy simulations. This will be my last slide. So okay, so this is a vector field in R3, okay, Euclidean space. As I said, being a Beltrami field, it doesn't have finite energy. No Beltrami field has finite energy. That's impossible. So it's natural to ask whether there exists stationary solutions of the Euler equation that simulate a universal Turing machine and that have finite energy. So for this, let's go to the torus. And you can ask the question for the torus with flat metric. So the enemy here is that it's a result which is very well known in computer science and connections with dynamics. Many people work about this, Daniel Grassa, Braverman, Rojas, etc. So the point is that there are no robust and Turing complete dynamical systems on compact spaces. And the physical interpretation and actually quantitative interpretation of this, but I'm not going to write the quantification, is that, or this can be understood in the sense that the finite memory of a physical system limits the size of the tapes that can be computed. And this is something that is called the space-bounded Church-Turing thesis. So, so the point is that this doesn't mean that there do not exist Turing-complete vector fields, Turing-complete stationary solutions of Euler or Beltrami fields on the torus. This doesn't imply it, but it means that in case they exist, they cannot be robust. I mean, their computational power is lost if you perturb it slightly, and it also means that it's difficult to construct. So what we were able to do is that restricting to tape size Turing machines, we can simulate with Beltrami fields on the torus. So if TB is a tape-bounded Turing machine, any tape-bounded Turing machine, then we prove that there exists a Beltrami field on the 3 torus, flat metric, of course, that robustly simulates this Turing machine, this tape-bounded. So the tape is no longer infinite now; it's just a finite number of positions, and this has a really dramatic energetic cost, which is this. It's not. It's that if you want to simulate tapes of size k, then the energy, and energy by energy I mean the H1 norm of the field, which is essentially the eigenvalue of the Beltrami field, it's a triple exponential x of the tape size of the Turing machine. So in particular, of course, we cannot take the limit. If you want to simulate a universal Turing machine, k is infinite. It's infinity because you have arbitrarily long tapes. But then when k tends to infinity, the energy blows up. So it's not possible with our constructions to construct a Turing complete Beltrami field on the torus. Okay, so I think I'm done. Yes, I don't know if there are some questions.
The lower bound, is that just for Beltrami fields or for?
Yeah, for Beltrami fields with our construction actually. This doesn't mean that. I mean, it could even happen that the ABC flow is Turing complete in subsets. I don't know. Yes. This is with our construction for Beltrami fields. This is the lower bound. And this cannot be improved within such a construction, but we don't mean that. And actually, if you compare with the quantitative estimates, with the quantitative predictions of this space-bounded Church-Turing thesis, this is very far from being efficient. So essentially, the quantitative estimation is that if you call the memory of the system, the memory is something. I'm not going to define it. Just let's think of in a very imprecise way. So the space-bounded Church-Turing thesis says that the size of the tape size is proportional to the memory. Is of order m. K is of order m. So this translated into this language would mean that in our construction, the K, the tape is of order log m. So it's very inefficient. So log m is very far from m. So this means that probably you could get better estimates for this construction, but not with our construction. Okay, so I think I'm done. Thanks a lot for your attention. I mean, sorry, I cannot go. I think it's a bit far there to go to the coffee break, but you can write me an email if you want.
Yes, thanks a lot. So there's some questions. Yes.
Can I take you back to the definition of Turing complete dynamics?
Sure.
It seems like there's a general lesson that one shouldn't ask infinite precision of any computational model. It usually leads to ridiculous consequences. And I'm concerned that the definition here has you start at a precise point. I mean, the output allows for error because the question is answered by whether the trajectory lands in an open set. But I'm concerned that the input has to be infinitely precise. That troubles me.
Yes, that's right. So yes, the output. So you have an open set. This is robust, say. But the point, I mean, but this is not an open-to-open definition. This is a point-to-open definition. So so you could okay. I can say that this is the usual definition for people who construct Turing complete dynamics. And actually, Terry Tao, when he constructed Turing complete diffeomorphisms of the torus and applied to the potential wells, etc., he considered this definition. But the bad point, as you said, of this is that this is not robust, and this is one of the reasons. This is one of the reasons why we have the enemy. Sorry, here is the enemy. That this is not that this Turing completeness in compact spaces. This Turing completeness notion is not robust. It doesn't persist under perturbations. So
this is a math lecture. So in effect, I'm not allowed to criticize the definition. But if I was in a physics seminar or a computer science seminar, I'd criticize that definition by pointing out that, for example, if you have a computational model that allows infinite precision multiplication of real numbers, then in polynomial time, you can solve any sharp complete problem. So that's a result from the 1960s, which illustrates when you pass the infinite precision, encodings are present that allow what I would say are absurd results.
Mm-hmm. Yeah, that's so there is you can change slightly the definition. So instead of considering P, just considering an open set, open to open, right? Exactly the same, but open to open. So then the point is, can we construct, or can people construct Turing complete dynamics with this, let's say, better definition? Let's say, I don't know if better, let's say alternative definition. So so most of the constructions don't use this definition. For example, the construction that Eva explained yesterday of a Turing complete system on the 3-sphere, you remember this construction? This we cannot do for sure with an open-to-open definition, but this construction, let me sit here. But the construction of our theorem here, this is not so. Actually, here we consider, because it's a very non-compact construction. We consider the trajectories and the Turing machines embedded on a plane, so non-compact. Then this construction could be adapted to open definition. And actually, in the proof, we use intervals encoding the Turing machine tapes. So open sets encoding the dynamics. So for this construction, this could work. Yeah, but it's non-compact. Yeah.
Just one final question about that theorem. I mean, it's great that the input could be made from an open set. That's huge improvement. What about perturbing the flow slightly? Suppose the flow is not exactly defined, but there's some error around it as well. That corresponds to a machine that occasionally makes a mistake. You know, in ordinary computation, you can error correct. You can still do computation with a machine that's not 100% reliable. Would that be the case in your theorem as well?
Yeah, so we allow for an error here. Is this your question? If we allow for
error in the flow, an open set
error in the flow,
open set around the definition of the flow.
In the definition of the flow,
The flow should not be infinitely precise either.
That's what he said.
But
U is perturbed with an error function. That's the second point, the last point, right? It persists if U is perturbed with an error function.
Great. Okay.
Isn't that the answer to
Sure. Yeah, it persists. I mean, since it's non-compact, you need to decrease. Why you need to decrease the error function? Because our open sets, if you want to think of the definition, our open sets are not uniform everywhere. They are narrower and narrower as you go to infinity, and then you have to decrease this. But it is robust in this sense. It is. Yeah. So you can think for this theorem, you can think of an open-to-open relation. Yes. But as I said, not for the three-dimensional construction that Eva explained yesterday. That's not robust at all. Yeah, for several reasons.
Still an infinite open set. I mean, it's an unbounded open set.
It's an unbounded. Yeah. One of the reasons is that, yeah, of course, because the construction of Eva was on the S3, and of course you cannot cover S3 with infinitely many, let's say, uniform open sets. That's impossible by the finite volume of the sphere. So yes, that's one of the very obvious reasons. Yeah.
Thank you.
Is there any kind of anything you can say about complexification? So it's a real analytic, so you consider like how to complex domain.
Yes. Well, this vector field is entire. Yes. So you can complexify. So it's in R3. It's analytic in R3, but there exists. It can be complexified to a holomorphic field on C3. Yeah, that's true. Yeah.
On the C3, the whole C3.
C3 on the whole C3, holomorphic, three holomorphic functions on the whole C3. Yes, that's right. Yeah. Because I didn't explain this. Sorry, it comes from the construction. It comes from the fact that we construct our field using a Cauchy-Kovalevskaya theorem, and the datum is a function that is already entire on C2. I mean, so you have all the computations on a plane, right? And your Cauchy datum is complex. It can be complexified. Then with our Cauchy-Kovalevskaya theorem, we get a field that is entire as well. It has exponential growth actually.
Yeah, but I was asking just in general, so when we talk about Beltrami fields, this complexification, is anything kind of useful to consider? What is it? Like we have Beltrami field, so it gives, say, given R3, and then usually it's extend to some kind of like, we can choose some like Stein neighborhood where it extends. And can you say anything about like, can you get any information about Beltrami field studying this holomorphic dynamics?
Studying the holomorphic extension. No, I don't know. So it's true that in general, okay, I'm not sure now if any Beltrami field can be complexified to the whole C3. This I'm not sure. That's true with some reasonable assumptions. I mean, if it's if it's polynomially, if the Beltrami field has polynomial growth, then it can be certainly, it is entire, it can be complexified. But okay, but your question is if you can use this complexification to prove, let's say, for example, this sort of theorems, right? Some sort of approximations, or because this reminds of a Runge theorem, right? No, I don't know. I don't know that this, it's never been used for sure, and I don't see now how a complexification could be used for these results. Yeah, I don't know.
Okay, I think we should stop and thank the speaker again.